guys,
Hi,
I'm Bronwyn
I'm Aaron.
and we're here to talk to you today about Week 5's prac. So Week 5 prac is a really good one.
It is. This one actually holds a little bit of significance for me.
Yeah, we're looking at blood glucose analysis. So how could that be significant to you, Aaron?
I'm a type 1 diabetic, so I actually have to get my blood tested quite regularly by a pathologist and also by my own little finger pricking tests.
So you're going to get the students to do it today for you?
Yeah, why not?
You up for the challenge? Let's see if Aaron's blood is within acceptable limits. So we're going to need a hypothesis for this prac. And of course, right here and right now, we are not going to feed that information to you, but I think we can give a few hints.
Something like, what is a healthy human's blood glucose?
So you aren't given this information, so you'll actually have to find out what a normal glucose would be. And then you can make a guess because you have no idea if this serum is from a patient that has diabetes or any other condition. So anything you say is going to be a guess, and make your hypothesis something that you can test.
Must be testable. And I can't help but stipulate, hypothesis comes before aims.
Yes.
Your aims are how you're going to go about achieving your hypothesis. Or proving or disproving, should I say.
So how are we going to test the blood today?
The most classic and widely used method is the Smoggy-Nelson method, which is actually a two-part process. First is a little bit of sample preparation, and then the development of the colour, which we'll be visualising in our spectrophotometer.
So we're going to be doing this on plasma, aren't we?
Yes. So blood is a complex biological matrix. It has lots of things. It has proteins, it has ions, it has carbohydrates. This is why to partition everything out and only get our reducing sugar of interest, that's our glucose, we need to do a bit of sample prep. And that's where the smoggy portion of the Smoggy-Nelson method comes into play, which is our deprotonation, so the removal of everything apart from our carbohydrates of interest. It is cloudy, it's a bit messy or whatever. If you go through and do your centrifugation like Claire does, which is coming up, or everything will be collected nicely down as a pellet at the bottom of your tube, and you're on the right path.
So Claire, our lab tech, allowed me to film her earlier in the week when she was preparing for this prac. So you'll be able to watch some of the things that she does and see some of the colour changes. So just have a little look at this next part of the video and listen to what she says as well. She has some really handy tips for you for when you're doing the prac.
We're first going to conduct a deprotonation step using the Smoggy method. We're going to grab 20 microlitres of our test serum, and place it in a 2 ml tube. We're then going to add 780 microlitres of deionized water. We're going to cap that and give it a quick vortex.
So the vortexing steps are really, really important. You need to ensure that each step your sample is mixed thoroughly before you add the next solution. If you don't do that, your solution won't work properly.
We're then going to add 100 microlitres of sodium hydroxide, and then after another mix we're going to add 100 microlitres of our zinc sulfate.
And it's very important that they're done in that order.
That's correct. And give it another mix. You'll end up with a cloudy solution. That's your proteins precipitating out. Our solution's now been sitting for several minutes now. You would then centrifuge the sample, and that allows all of the floating precipitant to move to the bottom of the vial. Here's one we prepared earlier. You can see that our precipitate is sitting on the bottom quite nicely, and on the top is what we call our supernatant. Now, for this reaction, our supernatant should be clear. If yours isn't clear, you need to repeat these steps again.
So the supernatant is the liquid.
The supernatant is the liquid on top of the precipitate, yes.
And the precipitate is also known sometimes as the pellet. You might hear that word being used.
Correct.
So what's the Nelson step involved then?
Well, the Nelson step is using a Nelson's reagent which contains copper 2+. We're actually going to change that to copper 1+, and then when we react it with our arsenomolybdic acid solution, it will reduce and cause a colour change to molybdenum blue.
Okay.
I'm probably not pronouncing that correctly. And that gives us our colour that we then, analyse in our spectrophotometer.
So I just love playing with copper because going from one form to another is a change in colour straight away. So you start off with copper 2+, is that standard blue colour. So you'll be seeing that today.
Mm-hmm.
We're now going to prepare a set of glucose standards. You'll notice in your lab manuals that you have 5 glucose standards. You have a blank and 4 standards with concentrations of glucose in them. I'm going to start by preparing my S4. S4 requires 200 microliters of our glucose stock standard. So you can see that our S4 is our most concentrated standard, all the way down to our blank, which is 0. The next step in the procedure is to assay duplicate lots of 0.2 ml samples. Now, when you're pipetting the supernatant, you need to make sure that you're not disturbing the pellet. Okay, we're going to take 200 microliters or 0.2 mils. And I put it in another Eppendorf tube. We're then going to add 500 microliters of our copper reagent.
So today we're using some really nasty chemicals, and these chemicals could be dangerous to the fish.
In particular, arsenic, which is in the arsenomolybdate solution, and copper are toxic, very, very toxic to aquatic life. So please think about the fish, and as Claire has suggested, don't put your reagents down the sink. Make sure they go into the proper waste containers provided.
You need to make sure that any copper reagent that's left over from your practical is put in a waste container and not down the sink.
So we don't leave it in the Eppendorf tubes?
We can leave them in the Eppendorf tubes provided you seal them and then toss them in the clinical waste. We're now going to vortex it to give it a good mix.
Today we're using 100-degree heat blocks, and this means that there's going to be quite a pressure build-up in your tubes, and you don't really want that build-up happening, because what can happen is the gas really builds up in there, causes the lid to pop off, the sample will pop out and could splat your face, or worse still, your partner's face. So you don't want that. So you're going to have to puncture the tubes. In this next little video, Claire's going to show you how to puncture the tubes. But just remember, it's the demonstrators that are going to look after the lancets, so you will have to go to them to get one.
So typically we'll pierce twice, being very careful with the lancet. Before we put the solutions in the heating block. After your samples have come out of the heating block, they need to cool. We will provide you with ice for this step. After they've cooled down to room temperature, we're going to add 0.5 mils of our arsenomolybdate reagent. Again, the arsenomolybdate is toxic to the aquatic environment, so this needs to go also in the waste containers that are provided, or back in the Eppendorf tubes that should be sealed before they're tossed into clinical waste. We take 0.5 mils of that and add it to our solution. You can see straight away that it's bubbling up nicely, which is what we would expect. We're going to now add 0.7 milliliters or 700 microliters of our deionized water. You can see that our volume in there is close to the top. You should have 1.9 milliliters in each of your tubes.
And you can tell that just by looking at how full your tubes are. So you can see there's not much room for any extra liquid in there. So make sure with each one you check your volume to ensure that you have done everything correctly.
Absolutely. So you can see that there's some gas bubbles built up in there already. For the next 10 minutes, you will vortex every 60 seconds or so the tubes. This just assists in the reaction and allows the gas bubbles to move up to the top. Now you need to make sure that you're not inverting your tubes, because remember, we've pierced our tubes with lancet already. So just a very gentle vortex, and then allowing that air to be released.
So if you have enough supernatant, instead of just doing a duplicate sample, you may want to think about triplicates. Triplicates just make everything a little bit more accurate.
And also checks your precision as you go. One of the key points is if you have two samples, one of it might be really high, one might be really low, and you don't know which one is actually correct. If you do a third sample, a triplicate, then you've got 3 points of data to compare.
And so then if you find that two of them are around the same reading and one's way out, then you can toss out the one that is obviously out of range.
Outliers.
Outliers, yes. So then you'll find your outlier.
I was going to say, they can skew your data sometimes if you don't really know about it. Kind of horrible.
Yes, so it's better to use a triplicate if you can.
Definitely. Once again, it's important that with all of your standards and samples and that you make sure that the volume that you're putting in is all the same. It's easily checked just by holding them up and looking to see that the same volume has been put into all the samples and standards.
And while you're holding it up, you can make sure that the colours of the samples that are going towards your standard calibration curve nicely change colour, starting with a very light one and going through to a darker colour.
Yeah, nice gradient.
So here's a picture of what the samples should look like.
Beautiful. Here's a photo of the spectrophotometer with the absorption spectra for the highest glucose standard, which is 0.06 micromoles.
So from this you can decide whether you think your spectrum looks okay. And of course, if you have any problems, make sure you speak to your demonstrator as soon as possible so we can help you fix things. So once you've finished doing your experiment, you then need to process your results. So of course, Perry has some notes on how to do it, but one of the most important things you'll need to be doing is a standard calibration graph.
So, what is a standard calibration graph?
It's the graph that's going to help you determine how much glucose is in your serum samples. So in this case, it could be in your serum samples.
How much?
Or even in mine, who knows?
How much glucose is potentially in my blood?
Yes, so the importance of it is that these are the points that you actually know the value for. So from this you can see the ratio between the absorbance of the glucose and the micromoles of the glucose. So once you have the standard curve and you have these amounts, it's then very easy for you to take an unknown sample with a known absorbance and read from it and figure out how much glucose is actually present.
Standard calibration graphs, very important.
They are indeed, and it's very important to understand what they're used for.
What I would like to mention in regards to these, make sure that your labels on your axes and your units are correct and well defined. Also remember to title the graph appropriately. It will be a figure. Anyway, we'll see you in the lab. Bye.